These are the solutions to activity 6. Just a reminder, the solubility chart's given on exams, so let's make sure we learn how to use this chart, but not necessarily memorize it. First question, which compound is soluble in water? So it just has to do with our solubility chart. So lead chloride's insoluble. It's one of these exceptions for chloride. Mercury 1, the Hg2 is also an exception. And so the only compound that's soluble here is A. I'm without a pencil right now, so this might look kind of peculiar because I'm writing just with freehand here. So only HgCl2 is soluble in water. Lead chloride and mercury 1 chloride are the exceptions for chloride that are insoluble. What is the oxidation number of Br and BrF5? The key is that fluorine is -1. There's 5 of them, so that makes bromine here +5. So we have to know our rules. Fluorine's always -1 in compounds. Now F2 is not a compound, so the oxidation number of fluorine in F2 would be 0. So in compounds, F's -1. O is usually -2 with some exceptions. Peroxides, superoxides, compounds with fluorine are its exceptions. The other halogens usually -1, except when they're paired up with O or F, where O is -2 and F is -1. Which compound property is incorrect? NH3 is indeed a weak base. It partially ionizes in water to NH4+ and ammonia. It partially reacts with water to form ammonium and hydroxide ion. The presence of hydroxide ion being formed in that solution is why we call it a weak base. HClO3 is indeed one of our 7 strong acids. HNO2 is indeed a weak acid. It's not one of the 7 strong acids. HNO3 is a strong acid. And then MgOH2 is indeed an example, is not an example of a strong base. It's insoluble. So this is insoluble in water. Because it's insoluble, it can't be any kind of base. So that's the incorrect property. Which atom is oxidized and reduced in the below reaction? So let's look for what's unchanged. So I see nitrate, nitrate, and nitrate. So it doesn't appear that the N or the O in nitrate is undergoing any kind of change. So we have nitrate here with manganese and iron. What is changing? We'll have iron 2+ here. How do I know that's a 2+? Well, iron's paired up with 2 nitrates. So that's how I know that's iron 2+. Then over here, iron is a 3+. And so iron's a 3+ with 3 nitrates, only a 2+ with the 2 nitrates. So iron goes from a 2+ to a 3+, meaning it lost an electron. So iron is losing electrons, is indeed oxidized. Whoops. So iron indeed oxidized. And then manganese is going from the KMnO4, where MnO4 must be a minus, and K is a plus. So we have potassium plus, O -2, -8 from the collection of 4 oxygens, +1 from the manganese. So we have a +7 for manganese. So manganese is +7 in the reactant side. And then on the product side, manganese is a +2. So we have, looks like 5 irons losing an electron each. So that's a total of 5 electrons lost from the 5 iron 2+. And then we have 1 manganese +7 gaining those 5 electrons. So 1 manganese is gaining electrons. So manganese is reduced. Nitrogen's unchanged. The H's are unchanged, plus here, plus here. All the oxygens are -2. In every example here, all the O's are -2s. So none of the H's or O's are undergoing any change. Likewise, nitrogen and nitrate is not undergoing any change either. What is the concentration of chloride ions in a solution prepared by taking 0.075 moles of calcium chloride and dissolving that into 425 mils of solution? The concentration of CaCl2 would be 0.075 divided by 0.425. So if I take this number of moles here, divide by 0.425 liters, and calculate, that gives me about 0.176. That's molar calcium chloride. Now, calcium chloride really isn't CaCl2 in solution. It's really calcium 2 plus, and then for each 1 mole of calcium chloride, we get 2 moles of Cl minus. So our concentration of chloride ion would be about 0.35. So 0.35 molar chloride ion. The total ion concentration, I get 3 moles of ion. So if I multiply this by 3, would be the total ion concentration. So we're just trying to think, ionic compound dissolves into solution. We're trying to think of that ionization reaction that's taking place, and then how many moles of chloride we get as a result. How much 0.1 molar HCl should be diluted to 125 milliliters to yield a 0.02 molar solution. So if I use MIVI equals MFVF, our dilution equation, because we're diluting 0.1 molar HCl, and we're diluting it to 0.02 molar, and then we're diluting it to a total volume of 125 milliliters. What do we want our initial volume to be? Well, we just do 0.02 times 125 divided by 0.1 would be 25 mils. Answer B. Question 7. This was in last week's notes here. We have how much KHCO3 here should be added to completely neutralize 250 mils of sulfuric acid. That would be 0.25 moles of sulfuric acid. So this amount here corresponds to 0.25 moles of the H2SO4. I need twice as many moles of KHCO3 because for every 1 mole of H2SO4, I need to add 2 moles of KHCO3 to fully react with it. So I need half a mole of KHCO3. So I need 0.5 moles of my compound, and it's 100 grams per mole. So I'm going to need 50 grams. Now, we're not covering titrations this semester, so this is just being shown as an example that, I mean, you can maybe recognize, like, I think it might be useful to see a problem that we're not responsible for, from the results of a titration while we're not covering titrations on exams. We can do more or less a similar type problem, or using the reaction we're looking at in a previous example. You can just get a sense that you don't need to work out an unknown concentration for these titration problems, and we can skip those problems. So another problem we're skipping is like an analysis. So I mentioned in class, something about determining percent by mass. We can skip those problems too. Now, we get into chapter 5 this week as our next chapter. And so what process absorbs heat and is endothermic? So endothermic is just a definition for a reaction that absorbs heat when it takes place. Exothermic is a reaction that releases heat, and is the opposite. Combustion, like this is like very exothermic. The flame of that reaction taking place is the heat being given off in the reaction. So the combustion of methane is a clear example of the opposite exothermic reaction. Now the boiling of water, if we want to boil liquid water into its vapor, we have to supply heat to water. We're going to put it on the stove so the water molecules in the liquid phase can absorb heat to break the attractive forces those molecules experience with each other so they can separate into the gas phase. So indeed, the boiling of water would be endothermic. So only 2. A chemical reaction that warms up its surroundings is said to be blank and has a blank sign for delta H. So a chemical reaction is taking place. Imagine we put like a compound in water, let's say. And the reaction is doing something in that solution, and then it's going to change the temperature of the solution. If the chemical reaction, imagine a compound is just dissolving. Let's say we put something like calcium chloride, I think is a good example. We put calcium chloride into water, and the water temperature goes up because the calcium is going to 2+, the chlorides are falling off and ionizing in solution. So this compound here going from a solid to an AQ, and in the process of ionizing, leads the solution to warming up. We can say that's an example of the exothermic reaction. So this is what it would look like to be exothermic. and then the sign of delta H is negative, and it's the delta H of reaction. So delta H of the reaction is less than 0. That's exothermic. So exothermic negative. And now let's think about what's going on here. What's going on is the reaction loses heat. Where does the heat go? Goes into the solution, goes into the surroundings. It goes into what surrounds that chemical reaction. The solution, the cup, like if you imagine the container that holds the reaction gets hot. That's because it's absorbing the heat that was given off by that chemical reaction. That's from a exothermic chemical reaction. Now let's think about the previous example on the last page of boiling of water. We said you put it on the stove. Now the stove had some exothermic reaction has to be undergone in order to heat up the water. Like we have to take maybe methane, burn it on our stove if we have a gas stove. And in that case, we're using a chemical reaction that releases heat to take the heat that's released to give it to some other reaction that can then take that heat and absorb it to do some other endothermic reaction. The enthalpy of water solid to water liquid is plus 6.01 kJs. What is the enthalpy for the below reaction, which is the opposite reaction? So we have to flip the sign, and then the magnitudes have doubled. So it should be 2 times minus 6.01. Minus because we flipped the reaction. So if we flip the reaction, we flip the sign. So this should be about minus 12.0. Last question, the combustion of ethanol proceeds as indicated below. How much heat is absorbed or released when a quarter mole of ethanol combusts? So this is obviously, we would expect exothermic, and this is exothermic. So we have an exothermic reaction. The reaction's releasing heat. The heat goes into like a flame as this reaction's taking place and the ethanol is burning. So ethanol plus O2 goes to CO2 and water. Just looking at the balancing. So if I take a quarter mole here, one of the things I might say is if you took an entire mole of ethanol, you'd get 555 kilojoules of heat released from this reaction. This reaction is going to release heat. A quarter of a mole, the way we can write this out, mole of ethanol, it should go this way. For every 1 mole of ethanol, according to that reaction, minus 555 kJs is the heat change in the reaction. So that's going to be 139 kJs. Now, negative means the reaction loses that heat. Where does it go? It's released into the surroundings. So the reaction releases 139 kilojoules of heat. Okay? If the opposite of this reaction, if this reaction were positive in delta H, then the reaction would have to absorb heat in order to take place. So endothermic reactions have positive delta H's, meaning that's the heat they have to absorb to take place. And then exothermic reactions, the reactions that release heat, and this one here releasing a lot of heat, is showing us the heat that's being released. I like to think of sometimes the questions in this chapter are almost always looking for the heat change to be positive in value. Kind of think about the corollary to a question of like, how much money did you win or how much money did you lose? Like you're implying the sign of the money change for your wallet or whatever by if you won money or lost money. And so if you lost money, obviously your money change was negative, and if you won money, your money change was positive. Think about that here with heat. We like to track heat. Where did it come from? Where did it go? So it's going from this ethanol as it burns to the surroundings. So the heat is flowing away from the ethanol. The ethanol reaction is causing a loss of heat from the chemical reaction taking place and a gain of heat to the surroundings. And so the surroundings is gaining the heat. So you can say, what's the heat change of the reaction? Well, minus 139 kJs of heat was changed by this reaction. And where was it changed to? Well, that amount of heat was released to the surroundings of that reaction. Okay, that's all for this activity. Thanks for the attention.